as the superset, which is equal to U minus A, or just A complement. This is the set of elements that belongs to U but does not belong to A. For example, let the universal set U, capital letter U, be the set of all numbers, that is U is equal to Y, that is such that 2 is less than or equals to Y, and Y is less than or equals to 16. Find the complement of the set X when our X is equal to small letter x, such that X is a member of U and X is a multiple of 4. Now we are to find, we actually use a set builder in defining these types of sets. So we will now define the elements in U. The set U is equal to 2. Mind you, it said 2 is less than or equals to Y, while Y is less than or equals to 2. That is, we start from 2 and we end with 16. They are inclusive. Thus, X is equal to, our U is equal to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And X is equal to 4, 8, 12, and 16. Then, the elements of U that are not present in X, that is our X complement, is equal to 2. We can find 2 in X, the set X, and then we have 3, 5, 6, 7, 9, 10, 11, 13, 14, and 15 are not found in set X. So we can easily say that our X complement is a set of elements that are not found in X but are found in our set U. Then we go to cardinality of sets. The number of elements in a set, say Y, is called the cardinality, denoted by N, small letter n, into bracket, capital letter Y. That is our set Y. For example, what is the cardinality of set A, which is equal to X, such that our 2 is less than X and X is less than or equals to 2. 2 is less than X and X is less than or equals to 16. There are 16 minus 2 elements in the set A, since X is strictly greater than 2, that is 2 is less than X, which means X is strictly greater than 2 and will be equal to 16. This simply means that there are 14 elements in the set A. Therefore, we can easily say the cardinality of set A is equal to 14. Then the next operation of set is union of sets. If M and N are two sets, then the union of M and N, denoted by capital letter M, union N, that is, the symbol being used is like a U but not U, is a set of all elements that are either in M or N or in both M and N. Using the set builder notation, we have M union N is equal to Y, such that Y is a member of N, or Y belongs to M or Y belongs to N, that is M union N is equal to Y, such that Y belongs to M, or Y belongs to N, or Y belongs to both M and N. For example, if set A is equal to 1, 3, 4, 5, and 10, and our set B is equal to 2, 3, 10, 11, 15, and 20. Mind you, 3 is repeating itself. Now, A union B, find A union B. A union B is equal to 1, we have 1 in set A, and then 2, we have 2 in set B, 3. We have 3 in set A and B. We are not to repeat it. That is, Y belongs to, 3 belongs to set A and B. Then we have 4 in set A. So we can easily say that our A union B is 1, 2, 3, 4, 5, 10, 11, 15, and 20. Mind you, there are some elements that belong to A, and then there are some elements that belong to Y, and then there are some elements that belong to both A and B. So we just combine all those 3 elements together without repetition. Recall that A union B is equal to B union A. That is, the operation union is commutative. That is, given the same result, A union B is equal to, is the same thing or is equal to B union A. Then the next operation of set is intersection of sets. If A and B, if sets A and B are two sets, then the intersection of A and B is a set of all elements which belong to A and B, denoted by A intersection B. The symbol there represents intersection, that is the symbol being used to denote intersection. That is, A intersection B is equal to X, such that X belongs to A and X belongs to B. X belongs to both A, set A and set B. This means that the intersection of set A and set B is a set of all X such that X is an element of A and also an element of set B. For example, if set A is equal to 1, 2, 3, 4, 5, and 6, and B, set B is equal to 1, 3, 5, 7, and 9, find A intersection B. A intersection B is equal to 1, 3, and 5. That is, we can find 1, 3, and 5 in set A, and we can also find 1, 3, and 5 in set B. Those are the elements that we can find in set A and set B. We can find 2 is in set A, but not in B, so we can't write it. It's only the element that we can find in set A and B that we are going to write. Remember that A intersection B is equal to B intersection A. That is, operation of intersection also is commutative. The next thing is for us to go, operation is Venn diagram, which is also a means of describing a set. Now, John Venn developed a method whereby a set can be represented diagrammatically. A Venn diagram is therefore a pictorial representation of sets. Operation of union, intersection, and complementation of sets can be shown by using Venn diagram. Just as we can see in the first diagram by the left, we have A union B. The two circles interlock each other, that is, B overlap A, and all the circles are being hashed. That is, there is a stroke on it, which is the same thing as B union A. Followed by it is the next diagram, which is A intersection B. Now, it's the point at which they overlap each other is the only portion being colored there. So, and the portion being colored shows the elements that are in A, which are also in B, and that gives us our A intersection B. When we are now having 3 sets, A, B, and C, that one gives us, the picture there gives us the possible representation that we are having. We have A, B, and C. We have B intersection C. We have A intersection C. We have A intersection B. We have A intersection B intersection C. That is, the element that can be found in set A, that can be found in set B, and found in set C, all at the same time. Now, according to what I was saying, the next diagram with color blue shading, we have A union B, then we have A union C. Now, A union B represents elements that are in A and B, and then we have elements that are in A and C. We are now considering bringing them together to find elements that we can find in A and B and also in A and C. So that means the elements in A is fully represented, but B and C are not fully represented, except the portion where they overlap. That is, element that can be found completely in A, and then partly in B, and then partly in C. So that gives us the color blue shading. Then the next one is A intersection C complement intersection B complement, and that's a portion being shaded. Here we are actually dealing with elements that can be found in A, not in B, that cannot be found in B, that cannot be found in C, but can only be found in A. Then we now have A intersection B complement. That one will, the portion being shaded gives us the element that can be found in set A, but not in set B. That is, cannot be found in set B, but can be found only in set A. That means the whole of set B is being removed from the portion. Then we also have A intersection B being colored green, being shaded green. That gives us elements that can be found in B but not in A. Whenever you see complements, it's telling you that element that cannot be found in a particular set, but when we now say intersection, then can be found in another set. Then A intersection B complements. Now we are taking set A and set B. That is, element that does not belong to both A and B. That is, common elements. We have elements in set A, elements in set B. A intersection B is the portion of the shaded. Now, element A intersection B, when we now remove that from A union B, that is the portion being shaded. That is, the elements A intersection B, by the time, whenever you see complement, that means it's not part of A intersection B, that is